speakers. Our next speaker is Kenneth Ma from Xilinx. Kenneth, great. We can see your screen. And
thank you. Can you hear me?
Yep, we can hear you too. So you're on.
Great. Thank you, Archana. Thanks, everyone. Hi, everyone. My name is Kenneth Ma of Xilinx. Very glad to have the opportunities to give an overview of the OpenHBI chip-to-chip interconnect specification to you today. So first, let's take a look at these slides in the many other ODSA presentations that you may have seen today. OpenHBI is part of the ODSA Open Die-to-Die Interface family of activities, as highlighted in the blue here. And other ODSA activity, including the reference design and reference workflows with the intent to build an ecosystem for the chiplet enablement to enable the open marketplace, as Papi has mentioned in his overview this morning. With that, just a quick introduction, and then we can get started. So OpenHBI stands for Open High Bandwidth Interface. The workgroup is kicked off earlier this year in the February 6, 2020. The goal is to drive the OpenHBI as a open, public, royalty-free, high-performance chip-to-chip interface standard. And the primary focus is to achieve the best-in-class figure of merit, including things like bandwidth per millimeter, energy per bit, and latency, etc. Most of us would agree that the chiplet-based architecture will be one of the main pillars in the post-Moore's Law era. But we also know that the major new technology initiative, like the chiplet-based architecture, will take a long time to proliferate. So OpenHBI leverages the JEDEC HBM3 for its I/O, its performance, and its features, but most importantly is the broad vendor support and the IP ecosystem that has been built over the years for the various HBM generations. We are hoping that this will enable us to have a faster time to deployment for the OpenHBI-based chiplet ecosystem. Current members comprises of the leaders in the system, silicon, IP suppliers, and also foundry, including Cadence, Google, Samsung, SiFive, Synopsys, and Xilinx ourselves. Several other companies are evaluating, including the major hyperscalers, cloud, and high-end networking, and also IP vendors to evaluating to join the OpenHBI at this moment. Currently, I'm the chair of the workgroup, and then Andy He from Google, he's the vice chair of the OpenHBI workgroup. Just a couple words about the workgroup structure. Due to the nature of the workgroup, we are operating as a closed workgroup with the prerequisites to participate. We need to be the OCP community memberships, but then due to the nature of the specification, we also need the JEDEC membership to join. And then contributors who want to participate will need to execute an contribution license agreement. And then at the end of this presentation, there are contact details if you're interested to participate and contribute. So, So OpenHBI has several key features that come into play by leveraging the JEDEC HBM as a foundation. First, we focus on enabling the multi-terabit per second high-performance chip-to-chip interconnect, as we mentioned. But then we will be focusing on using interposer for high-density, interconnect, and then that can be like silicon interposer or wafer-level fan-out or similar. The interface is defined as a symmetric, multi-channel, scalable interface. By symmetric, it means that the OpenHBI itself does not have the notion of either master or subordinate, initiator, or target. It is a symmetric transport that can be mapped to upper layer, which will then be determining how the end-to-end protocol works. The basic building block of the OpenHBI, we call it the D word or data word. A design can scale by as many D word channels as necessary to meet the use case requirements. Each D word has a total of 48 signals, with up to 42 of them are data signals, with clocks and optional the data bus inversions for lower energy per bit, and then the parity and then repair support kind of additional signals. And then there are different modes and configuration that can be allowed to use the signals. Each D word is either TX for transmit D word or RX receive D word. If an implementation supports bidirectional D word, then the D word can be configurable as either TX or RX at boot time, but also optionally can configure at runtime. So the I/O is optimized derivative and electrically interoperable with the JEDEC HBM3 I/O. Data rate is up to 8 gigabit per second, nominally up to 3 millimeter with a maximum of 4 as allowed by the spec. And then the expected energy per bit will be less than 0.4 for nominal implementation and can be much lower than that. The bandwidth density is at least 1.5 terabit per second per millimeter with a configuration using 36 of the data signals of the D word, or 1.7 terabit per second per millimeter if you use 40 data signals. With the other, we mentioned 42, and the other 2 signals can be used for, like some framing or parity, and then depending on your configurations. OpenHBI is defined as a multi-layer architecture which will ease the adaptation to the upper protocol layer. More details later. We have some slides about that. And then on the last bullet here is OpenHBI has a unique feature that because it is HBM interoperable I/O and then HBM based, it allows the design to support optional implementation-specific dual-mode host, which can support both HBM free memory chiplet as well as the OpenHBI chiplet. So as shown in the right here. So, so this is an ODSA stack concept diagram. We also have seen many times. You didn't see much of the things above the OpenHBI rectangle, as it will be pretty busy. But OpenHBI does support the flexible ODSA stack vision as shown. OpenHBI is a multi-layer architecture, enables a simple adaptation layer to upper protocol layers such as the PCI Express, C6, CXL, or supported on-die protocols such as the AXI streaming, AXI memory map, or TileLink. OpenHBI also intend to support the ODSA open link layer shown in this box here, or and also plan to support the LPIF-based transport protocol agnostic interface in here. Both of them are actually in definitions, but we fully intended to support them when the definition is done. So this slide is a summary of the OpenHBI figure of merit based on a Y pitch of 55 micron. The Y pitch is defined as the microbump to microbump pitch in the direction along the die edge of the chip-to-chip interface. The pitch front height and depth dimension listed here of 6 millimeter times 1 millimeter is estimated based on a 8 high, 4 wide D-word array, meaning that this is a 32 D-word array structure. It's just an estimate. Implementation can have some variations there, of course. The I/O is a 0.4 volt unterminated I/O, and again is HBM free compatible. With 40 data signals at 8 gigabit per second, the HD word can carry 320 gigabit per second, and you can do the math that the 32 D word can give you about 10 terabit per second, and we can deliver 1.7 terabit per second per millimeter bandwidth density. Just to clarify, the bandwidth per millimeter figures here, they include all the bandwidth of all the D word, whether they are configured as a TX or RX, and all the ODSA D2D PHY is defined the same way. While we are working on the OpenHBI 1.0 right now, the work group is already planning the enhancements to the OpenHBI data rate and the figure of merit beyond what we are showing here, and of course in a backward compatible manner. So finally, the bandwidth per millimeter will increase further if the implementation choose to use a smaller Y pitch, which is allowable by the respective packaging technologies. Then the corresponding bandwidth per millimeter, of course, will go up because now you have a shorter pitch front. Okay. So to build an ecosystem, however, to offer truly interoperable cross-vendor chiplet ecosystem, we need much more than a die-to-die or chip-to-chip PHY specification. We see the following are required at a minimum. First, the spec must support flexible mapping to the upper protocol layer. Second, it must define an architecture for chiplet integration and mechanical alignment. We cannot just have a whole bunch of chiplets just randomly placed along any die edges, and then they won't work together. And also the dimensions, they have to have some guidelines. It must support any chiplet orientation on any die edge of the anchor or the SoC, meaning that if you put the chiplet on the different side of the chiplets, they will continue to work and continue to be routable. And to the extent possible, the specs should facilitate non-good die testabilities. So we defined the OpenHBI specification to include at least the following. Standard defined or recommended signal usage at the chip-to-chip physical interface level. Standard defined or recommended signal mapping to the upper layers. And then the integration and scalability rules and guidelines between different anchors in the chiplet. And the term anchor that are used, you may call it the host or SoC, but conceptually the anchor is the chiplet that can serve as a configuration master that can configure other chiplets in the package device. The orientation independent compensation is features that we support in order to enable, if you have a misorientation, that we would have a slide that talk about that, then we will still have this compensation to allow the completely seamless and straight connections on the interposer, and then while the lane repair capabilities are maintained. So lastly, we also have a standard-defined and recommended chiplet configuration and test interface, which will help to facilitate the non-good die testabilities. So with that, just a quick summary of the specification development status. We won't go into the details here, but you can get a sense of the key areas that OpenHBI spec is planning to support beyond a PHY specification. So we defined the DRAM array structures, we defined scalability integration guidelines, the multi-layer, including the PHY layer, the logical layers, they are fully defined. And then, so we're already making major progresses there. The IO electrical and the BOM maps, the clocking, we also will define the configuration and management. And then all are in progress right now. In fact, they'll make a lot of additional progress since I prepared this slide deck and the testing. So this slide shows a little more detailed view of the D-word. There are 48 signals, plus the necessary microbumps for the PDN or power delivery to achieve 8 gigabit or higher data rate. The figure shown is a virtual BOM map target here. By virtual, we mean that we don't have to follow exactly that. I mean, we all have seen how the SoC has been designed to support HBM. So as long as you can enable the the seamless routing and then hit all the figure of merit and required features, then you can design your own BOM map towards this virtual target. So in the previous slide, I mentioned that if an implementation can support bidirectional D-word, the D-word can be configurable as a TX and the RX at boot time. And however, for the chiplet that have a known or fixed configuration for specific use cases, they can design the D-word as a fixed direction or fixed personality for a more cost-effective as well as a more power-efficient design with a unidirectional I/O if they want to. So of course, a configurable D-word will allow for flexible configuration such as balanced 50% TX, 50% RX, or all TX on one side or all RX on the other side of the chip-to-chip link, or any combination in between, such as the asymmetric unbalanced configuration if the protocol layer allow you to do so, which Ken Poulton in this BOW talk also talks about that. However, the unique features of the OpenHBI that allows the optional configurability at the runtime is that it should be attractive for the cloud and hyperscalers use cases, as the accelerators, for example, they may operate on very different workloads at different time of the day, which may need to be optimized for different TX or RX traffic with the OpenHBI D-word configurability, meaning that when you change your acceleration workload, you can change your configuration as long as your accelerator is designed to tackle the different workload dynamically. So this is pretty interesting features that the OpenHBI can support. So this slide shows an example where the anchor die can have a multiple chip-to-chip interfaces on the beachfront here on the green, and then they can support multiple chiplet placed side by side in the red beachfront. We just sort of put the different colors to let you see clearly. This is the two examples where you have two different dimensions of the chiplet, but then we have definition and rules to ensure that they will align properly so that they don't have a major misalignment when you have a multiple chiplets be placed onto a single chiplet. So for that, so we have a standard defined and recommended the D-word dimension, height, depth, granularity of increments, again, the D-word array structure, and the provisioning of the config and test interface for each chiplet. And this is one of the elements we defined to enable cross-vendor interoperabilities. So this slide shows how the OpenHBI PHY layer and the logical PHY layer fit into a multi-layer architectures. Pretty simple, I think. The PHY layer will have the I/O circuit, clocking, gearbox that perform the serialization and deserialization between the I/O data rate and the slower internal logic clock domain. It can perform training calibration and to maximize the data I and the timing margin. OpenHBI also support the lane repair function, which is, by the way, same capability as the HBM3 lane repair capabilities in case they are broken or weak connections that need to be repaired. The logical file layer, which is above the file layer here in the green color, it performs what we call the bit reordering functions to enable the orientation independent routing. So it can support optional DPI or database inversions to reduce power, the priority for data integrity, and then framing and alignment to properly deserialize the incoming serialized data by the TX side gearbox. And of course, the optional ECC and FEC can be optionally implemented, or we can use the protocols layers up. They have the corresponding link layer, which can also perform the data integrity function in the layer above the OpenHBI. So the logical file layer, again in the green here, can map to the protocol layer directly or through the protocol adaptation layer shown in the orange color here. On the other hand, the upper layer, the protocol layer, can bypass the logical file layer and can use the I/O and the file layer, the blue color, directly as a bunch of wires if it prefers. So it's pretty flexible, and then they are bypassable. This diagram is just a simple illustration of how the application logic on the anchor on the left and can map through a layered OpenHBI chip-to-chip interface towards the chiplet logic, chiplet specific function on the right, such as the AI accelerator, co-package optics, networking functions, as shown in the diagram here. So this is my second last slide. We talk about our orientation independent routing support. So in case it is not clear what it means, this slide uses 3 scenarios to illustrate the concept. First, I'd like to clarify that the OpenHBI is defined such that if the anchor and the chiplet both follows the spec convention, they will always be in the proper orientation to enable seamless and strict connections on whichever die edge of the anchor they are placed on. However, if a design allows a chiplet to connect to itself, such as on the lower left diagram in the case 1 here, then it will result in a rotated orientation as shown. Or for case 2, if a chiplet, for whatever reason, choose to use a different orientation or put the bit front on the opposite die edge, it can cause the rotated orientation between anchor and chiplet, such as the green chiplet 2 as shown here. And we kind of highlighted the misorientation using the dotted line boxes here. So you can see the A, if you use it to depict orientation, they are pointing in the wrong directions in the both edges here. For case 3, if an SoC or anchor support clustering, such as a multi-socket GPU or CPU or scalable accelerators, they will also be in the rotated orientation as shown also in the red dotted line boxes here. So in all these scenarios, OpenHBI supports seamless, strict connections, which would otherwise unroutable as all the signals will be crisscrossed. So OpenHBI, the bit reordering function, will compensate the rotated orientation and readily enable such topology while continue to support all lane repair functions in any orientation combinations. So we define the lane repair functions to support the bit reordering mode as well. So this is another key element to enable the cross-vendor interop for OpenHBI-based chiplet ecosystem without having to co-design every step of the way, which is not always practical. So this is my last slide, summary and call to action. So OpenHBI leverage a proven, widely adopted HBM as a foundation of the chip-to-chip interface. Our focus is on high-performance multi-terabit per second applications with a very low latency in mind. Goal is to build an ecosystem that aligns with the ODSA's goal of the interoperable third-party OpenHBI chiplet. So we architected the whole thing with the layer architecture to ease the protocol mapping and several additional rules for the cross-vendor interoperabilities. The orientation independent is to enable the different chiplet orientation and anchors to interop with the lane repair capabilities maintained. The unique dual mode allows a design to support using the same interface to support both the OpenHBI chiplet as well as the HBM free memory chiplet. And this is optional and implementation specific, but the capabilities is there to allow you to do so. So you can then build a design that can use a memory intensive applications for one skill, and then you can build a IO intensive or accelerator intensive for the different skill. Configurable, the TX and the RX steward either at boot time or runtime enable the composability and dynamic configuration. Again, this should be pretty useful when you have many different workloads to deal with. Substantial figure of merit enhancement beyond the OpenHBI 1.0 is currently planned. So for now, we are planning the version 0.5 specification by the end of this year, and then the version 1.0 by the middle of next year. If you're interested to contribute or participate, please contact Bapi or myself, Kenneth Ma, or Andy He of Google. The contact is shown here. Thank you very much.
Hey, Kenneth.
Yep.
Since you finished amazingly early, there's a question on the thing about whether the announced acquisition by AMD you think will have any impact on this work.
I cannot comment anything on that. So at this moment,
Okay.
sorry.
Well, thank you so much. On the money as always.
Thank you. Thank you very much.
Thanks, Kenneth. Our last presentation